To lecture 25. Okay, so today we'll finish off the translation of LPMLN to ASP and start the next item, which is ontologies and description logics. Okay. So the only thing that was left in the relationship between LPMLN, MLN, and ASP was only this one. So how do we convert from LPMLN to ASP? And the translation uses so-called weak constraint, which is defined in the standard language of SSL solvers. So this is part of the ASP Core 2 language, which is the standard that modern ASP solvers follow. So it is actually built-in construct. So this is probably that you haven't seen, but it's actually quite simple to explain. This is called constraint. So like the constraint that you saw, this one, okay, it doesn't actually introduce new stable models. When you do this, you're trying to differentiate some stable models. So in the so-called hard constraint that you saw before, adding the constraint, if the stable model violates the constraint, they will be removed. Now, with weak constraint, the stable models are not eliminated by violating this weak constraint, but they will get some penalty. Okay, so that way you can distinguish between which stable model is more optimal than others. Now, weak constraint itself doesn't have notion of probability. It's in fact quite simple assignment of penalty to each stable models. Okay, but we'll look at this one first, and then use this construct to show the translation from LPMLN to ASP with weak constraint. So what is the syntax? So here F is a conjunction of literals. So by literals we mean that atoms and their negations. Okay, so P or NOTP, okay, and their conjunctions. Now, weight is an integer. So there are actually two numbers that you put in the square bracket. So the first one is weight, and it is any integer. You can have negative numbers as well. The second one is non-negative integer, so starting from 0, 1, 2, 3. Now the second one I denoted by the level. So this is the level of the preference. So when you are getting into this level, first, so I'm going to explain this in a moment, but roughly speaking, there is some notion of levels. And each level, you will get some penalty. Okay? And in the end, you will actually consider both level and weight to see which stable model gets more penalty and which are more less penalty. So least penalty stable models are the optimal stable models. And that's what Klingo computes at the end. All right. So the idea is this: when F is true, when the stable model satisfies this conjunction of literals, we say the weak constraint is violated, same as what we did for the hard constraint. And at that time, we don't actually eliminate the stable models, but we apply the penalty of weight at that level to the stable models. Okay. Now the level is going from 0 to 1, 2. So if you have higher levels, that means you have more, that thing has more priority. Okay, so you don't want to. If you can do, so suppose there are two stable models that breaks level 1 and level 2. Okay, so two different stable models. One violates level 1, the other violates level 2. Okay, then you prefer the one that doesn't violate level 2, so you prefer the level 1 one. Okay, so and inside the same level of the weight will determine. So we'll actually look at the semantics, formal semantics. So on this, let's assume that the program is union of these two. So one is pi1, which is the usual ASP program that you have seen before. And now pi2 consists of only the weak constraint. Okay? And when we say a stable model, we are only looking at pi1, the standard ASP part. Okay? And then for the stable models of pi1, we are going to associate it with penalty. And penalty is defined by this function penalty I, L, where I is the interpretation, and L is the level. Okay. So this is the definition. So at particular L, and this must be capital L, at particular level L, so suppose you have this weak constraint that talk about this particular level L, and the interpretation happen to satisfy this conjunction of literals. Then we will assign W, or some of the old W that satisfies at that level. The penalties at that level will be summed up. Okay, so look at all the weak constraint that mentions level L, this particular level L, and look at where this interpretation I satisfies the conjunction of literals there. If it is, then add W into the current accumulation. Okay? Okay, we'll look at the example in the next slide, or actually here. So that might be easy to see. So here we can think about this as pi 1 and this as pi 2, right? So pi 1 is the standard program. How many stable models are in pi 1? There are 4, right? So this is a choice rules. So every one is so everything is a stable model. Okay? All right. So let's look at the table. Interpretation, okay, or stable models here. So there are actually 4 stable models, and for each of the stable models, we are going to compute the weight at each, penalty at each level. So penalty at level 0, because there is this constraint has level 0 constraint. This one is level 1. So there are actually 2 different weak constraints. Okay, so let's compute this together. So when I is empty set, okay, what we do is look at, for this entry, okay, look at the level 0 weak constraint, which is only the second rule here, right? So what is the, so we have to see whether this interpretation satisfies P. Does it? So empty set, does it satisfy P? No. So then this constraint is not violated. This only one level 0 weak constraint is not violated, so you don't actually get the penalty. That means you are getting the number 0. Okay? What about level 1? So for the same interpretation, level 1 weak constraint is this. Does empty set satisfy now this Q? No. Again, it does not get the penalty, so it gets 0. Okay? Okay, so the next thing is going into P. Okay, so does P satisfy the level 0 one?
Yes.
Yes. So what is the penalty that it received? 10. What about level 1? 0. Okay, because level 1 is about Q, so P does not satisfy Q. So it does not get the penalty. What about the next one? 0. Now this one is 5. And this one? 10. 5. Okay, good. So these are the things. Okay? So we can compute levels, penalty at each level. Okay, now the next thing is, we didn't actually say how we select the optimal stable model, and this is the definition. Before we define the optimal stable model, we are defining which one is better. Okay, so we'll talk about the relationship between the 2 stable models. So say we have I and I prime. We say that I is dominated by I prime if this relation holds. Okay, so first, penalty that is assigned, so it is about some level, so there exists some level L such that the the penalty of I is actually bigger than the penalty of I prime. Then we say that I is dominated by I prime. Okay, in other words, I cannot be the optimal one, right? Good. On the other hand, you also need to say that about the levels, how these each different levels are actually related. So all levels are greater than k, their levels, their penalties should be the same. Okay, so what we are doing is checking at the highest level. If they are equal, the tie breaking goes to the next level, and so on and so forth. Okay, of course, if I is dominated by I prime in the highest level, this second condition is vacuously true, because for all levels greater than k, there is no such k, so that means this condition doesn't have to be checked. Okay, so in other words, if we want to find whether I is dominated by I prime, go to the highest level and check the penalty at the level. If there's a tie, then go to the next level. Okay, if I is penalty of I is greater than I prime, then I is dominated by I prime at that level. Okay, if not, then you continue until you hit. Are we together? Okay. So a stable model of pi is called optimal if it is not dominated by another stable model. In other words, if there is no other stable model that has less penalty. Okay? Okay. Okay, I think. Okay, let me skip this one for now. Okay, so how we use this idea to do the translation from LPMLN to ASP. So in fact, this translation is very simple. Okay, each rule in LPMLN is replaced by 3 rules in ASP. Okay, so we'll see how it goes. So given the rule of this form, Wi, head if body, okay, so first what we are going to do is note here that this rule has a potential to be defeated, right? It can be untrue or unsatisfied, right? So we say onset I is true if body is true but the head is false. When that happens, then onset atom becomes true. And we use this onset atom in the body of this rule, okay, which is similar to the original program, but now we put onset into the body, okay, with negation. And the second rule is read like this. So head if body if the rule is satisfied. Okay? So let me repeat. If this condition, if this body fires, that means body is true and the head is false. The rule is actually false. The original rule is actually false. In that case, onset atom becomes true. Now when onset atom becomes true, then this body becomes false. This whole body, these two, right, will be false, so that this rule does not, this rule can be ignored. Okay, when the body is true and head is false, we want to ignore this rule. And that is done by using this auxiliary atom called onset. Okay? Now let's talk about the other case. What if body is either false or head is true? Okay? Then onset is false, right? If body is true, body is false or head is true, okay, then this whole here, the body of this rule is false. So that onset I cannot be true. Onset I cannot be derived in the stable model. If that cannot be derived, then this becomes true. NOT of onset becomes true. So then when body is true, head must be true. Okay? So you can think about these two cases. Case 1, when body is true and head is false, then overall effect of this one is same as head if body. Right? But now when body is false or head is true, then the overall effect of these two rules is nothing, as if you're just dropping this rule. Okay? So instead of dropping or adding the rules as in Markov logic, you can actually think in terms of the divisibility in SSL programs. Okay? So together, these two rules together can be doing the same effect as head if body when the rule is true. Okay? When the rule is false, the rule simply is ignored. Are we together? Okay. So then that gives us one part of the translation where we can assume that the rule exists, or we can also ignore this rule if necessary, right? Now, how do we assign the weight to this probability, to this case? Here is the case. If onset becomes true, then this rule will get the weight Wi, the penalty Wi. Okay, actually I didn't introduce the level here yet. When the levels are actually missing, by default the level is actually 0. Okay? Okay. So when onset becomes true, it will get the penalty Wi. Okay? So this is actually one kind of translation. In fact, there are actually two modes of the translation. This one is actually more complete. So let's actually do this. The first one is same as what you saw in the previous slide. Now I put explicitly at 0. This one applies when Wi is any real numbers. Okay. Now when the weight here is alpha, which is to denote infinite weight, then what we do is we put this into the level 1. So when this hard rule is violated, then it will get more severe penalty at the next level. Okay? And at that level, it actually does not matter which weight that you assign, so we just put 1 there. So I didn't actually introduce proof here, and although this looks a simple translation, there are actually some subtle ideas behind it. And if you're interested, you can go to the link to the paper that explains this translation. But otherwise, I don't want you to be too much overwhelmed by all the technical details. The main message here is using this default negation, NOT, you can actually easily implement the idea of defeating the rules. Okay, so either including the rules or deleting the rules. Yes.
So when we have like more levels in the soft rules, let's say 0, 1, and 2. So then we assign level 4 to hard rules?
No. So that's an interesting question. As far as LPMLN semantics is considered, we need only 2 levels, because in by definition, the weight are all the real numbers in the same level, right? So all the real numbers weight are the same level, level 0. Okay, we only need that because those weight are total order, right? Now, when you go to the next level, you need the next level when you cannot compare, or when this infinite weight dominate all the real numbered weight. Okay, so that way you need actually 2 different levels to do. But as far as LPMLN considered, you don't need more than this level.
So
Okay.
in previous example, like we had level 0 and level 1. So can we consider the second one was the hard rule actually?
Kind of, yes. Yeah, that's analogy. Okay. In fact, when you use weak constraint, you can use up to as many levels as you want. Okay. Note here that the difference between weak constraint and this use of weak constraint in the translation is this. In the weak constraint, there's no notion of probability. Okay. There's no notion of infinite weight. Okay. There's no notion of how this weight will be converted into some exponential function. Right? There's no such thing. On the other hand, it is somewhat more flexible in some sense. You can have multiple levels. The main, actually, I didn't have time to go into this, but the main use of weak constraint is to denote some preference. So you want to prefer this stable model over that model, that stable model. Then you can introduce any levels, right? So between the same levels, you may have tie, right? That's actually happened in many preferential reasoning. So if you prefer A over B versus you prefer C over D, okay? Between A, B, and C, D, you have the strict order there. But between A and C, or A and D, or C and B, you don't know which is more preferable. Okay, so that kind of preference can be represented by introducing multiple levels. Okay, yes.
So I got two questions. So first, the translation where we are writing two rules, unset and head. So that is same as saying if body is true, choose exactly one of these two.
I'm sorry. Can you repeat?
So instead of writing two rules.
Instead of writing these two rules.
Yes. I would have written like choose exactly one from unset I or head I if the body is true.
Oh, you're suggesting some different encoding.
Yeah, I'm saying if that is same. So a choice rule I could have written, which head contains two items, unset I and head I, and has to choose exactly one.
I think that might be possible. In fact, if you go to the paper, there is a use of choice rules for the whole rules. So there are actually a few different levels of translations, and this is the last translation from there. But in the intermediate level, we actually have the version that uses choice rules.
And one more question is, why do we need unset I for hard rules? It should be always satisfied. So
no.
Just carefully.
We actually talked about this in the last slide, last time, when there are actually sometimes we want to violate hard rules. Right? Remember the bird example, sometimes you want to ignore hard rules. In that case, you need this. So, but the thing is this, I actually introduced these two different translations that we only translate soft rules versus doing both. And as I said, LPMLN to ASP support both mode. Okay? So most of the time, we don't want to violate hard rules. In that case, we will actually use this translation. That's actually one of the modes of computation. But sometimes you want to overwrite also the hard rules, then you go into these two levels. Okay? All right. Any other questions? Again, if you're interested, you can try to prove it. Okay? And in fact, the proof is also given in the paper, so you can compare this. Okay. So right here. Okay, so this is the example for the theorem. So suppose you have LPMLN program where we have alpha and 10 and minus 20 as the weight. So here we want to find most probable stable model. Actually, let's do the quiz. Okay, so I'm going to give you, and you will need to answer what is the most optimal stable model there. Okay, you can discuss with your peers if you want. So the question is, you have 3 rules. The first one is hard rule, and the second rules are the soft rules, with a positive weight and a negative weight. So what is the most probable stable model? Okay, are we there? Or need more time? Okay. What is looking at? Okay. Only 12 answers. Okay, so let's just look at what we have so far. P, PQ, P, empty set 1. I don't know where the 1 comes from. PQ, P, okay. So PQ, what? This was a keyword, not the okay. All right. So PQ seems to be the dominant answer there. Is it? Actually, let's try the implementation. I don't have this. So in the input language, I can just type P. I don't need to type alpha. So 10Q if P times 20Q. Okay. Okay. So this is LPMLN 2 ASP. Inside T minus out. Okay, so the answer is P. Why? Why PQ is not an answer? Let's go back. So P is the only, P is actually the most probable stable model. The reason for that is, of course, if you have a P, what is the weight that it receives? What is the weight that you get? Okay, so this one, P, what is the weight of this interpretation P? E to the power of alpha, right? What about PQ? E to the power of alpha minus 10. Okay? Right. So let's actually see. This is a translation. And as you see, for P, okay, so this is the rule with no body, right? So when this rule is false, meaning that P is false, so not P. then onset 1 becomes true. This 1 denotes the rule index, okay? And P is true if onset is false, meaning that if the first rule is true, then P should be true, okay? And this one is saying that if the first rule is not true, then it gets the this penalty. Okay, the penalty here is 1 at 1 because this one is the level, and this one is actually just same for all the hard rules. For the next one, you get the same translation, similar translation, except now this level 0 constraint with the weight 10, and similarly with this. So if you do this, it will find this solution. So here, as you see, the optimization will give this value. Okay, I don't know what. Yeah, I'm not sure why 0, 10. Maybe this. I think it should be. Yeah, it doesn't show here, so maybe. Yeah, okay. Anyway, forget about that thing. Maybe there was a typo here. All right. Okay, so having done this, that was only find the most probable stable model. You can also easily compute the probability. And this is done by looking at only the onset atoms. Okay, so in the stable model, you will see that will generate this onset atom. Okay, in the more general case, we are going to record the weight here as an argument of this onset, and looking at this onset atom. So the first index I is the index of the rule, Wi is the weight of that rule, and C is the ground instance of the grounding of the variables in the rule. So if the rule is non-ground rule, it will generate multiple ground rules. Okay. So for the previous example, we don't have variables, so you can ignore this C. Okay. So what that means is basically you look at all the onset atoms and extract the weight from there and add them up, and doing e to the power of minus. Now note here that this is not the exactly the same way that you do the weight computation in LPMLN. It actually uses the reformulation of the semantics that you flip the value, but that detail you don't have to worry about. Okay, but the point here is you can actually compute the weight of the interpretation, which is actually slightly different version of weight, which is so-called penalty-based weight in this way. But after then, you can compute the probability in the same way. Okay, you can probability of the marginal probability is to just add up all those probability. Okay, and conditional probability is also the same. Okay, and that's actually the whole idea about this system. So here, the input LPMLN program is simply a modification of a Klingo program where you just insert the weight in front of it. Okay, and the translator turns the LPMLN language into the ASP language, and this translation is basically turning each rule into 3 rules. That's it. 1 LPMLN rule turning into 3 ASP rules. Okay, so it's not explosion in the translation either. And then you call ASP solver. Actually, the Klingo is called. There's a post-processing module, which is to look at the onset atoms and extract the weight and do the probability computation. So the output, it can be actually used for 3 different things. You saw it can be used for computing the probability, as well as you can enumerate all the stable models and looking at their probabilities. Okay, and it can also return only most probable stable models. And as is the case in general, this computation, most probable stable model computation, doesn't require to generate all stable models, and it can be computed quite quickly, or most of the time. Okay, and for this one, the system actually supports 2 modes. One is easy thing is you just generate all stable models and do the normalization. So basically, as you do in the homework, you have to look at all possibilities and computing the normalization based on adding up all those weight. That's actually what is being done in one mode. But there is another mode which is to use the sampling. So it generates samples of answer set and then approximate probability from the samples. And that's again something that you saw before. All right? Question? Yes?
For the
Previous
previous slide.
slide?
So here, and the previous so here, do we count the 1 or alpha? Because if we
Do we count what?
so for the first one, the hard rule, did we count alpha as a bait or 1 because we have?
Oh, alpha is, yeah, just we count into 1 at 1. All the alpha rules will be assumed at level 1. And this one is actually arbitrary number, as long as you give the same weight for all the hard rules.
So in the next slide, when we are summing over all the weights, we are here.
Oh, yes, that's a good question. This one, yes, we do. Yeah, so that will actually generate e to the power of alpha. Okay, so that is actually dependent on probability computation module. It actually computes that limit using Python code. Okay. All right. Okay, so what we saw so far is this language is actually intermediate level, combining the strengths of different communities work. So in terms of knowledge representation, we actually look at the ASP. There's also another version of language called plog that extends ASP with probability. But we can actually capture these things into LPMLN, as well as statistical relation learning, MLN. We didn't actually go over ProbLog and PCM, but that can be also captured in LPMLN. So if you go to the paper link, you will see more translation of this kind. Somebody asked about intervention or causal model. So that's actually this direction. Okay? All right. Okay, so we are done with LPMLN now, and the next thing, maybe 1.5 lectures, what we are going to do is this one and this one. We are not going to talk about this. We don't have time, and this is our neural network course, but many of you already know some basics of neural network, and that should be enough. Okay? All right, so let's talk about ontologies. So what is an ontology? It's not philosophical terms, but it is actually kind of transformed into computer science terminology in some different ways. So ontology is a formal, explicit, shared specification or conceptualization of a domain. So what is a conceptualization? So it consists of these objects and the concept and other entities that are assumed to exist in some areas of interest and the relationships that hold among them. So basically, you just talk about object and relation, and that sounds somewhat similar to what you learned before. Do you recall what are the things that what was the formalism that we talk about objects and relations? In our course, we talk about first order logic, right? The first order logic, we have object or individual. We can name them, and we can have a relation which is a predicate. That was the foundation there, right? So foundation of KR languages that we talked about. And no surprise, the ontology languages are usually based on first order logic. Okay? So this, the term is borrowed from philosophy, and we are not actually using the same idea, but it's basically like ER diagram or whatever the concept relations that we can do. Okay, so this ontology today is a synonym for a shared knowledge base. So ontologies are typically expressed in some formal logic-based language, like first-order logic. The problem with first-order logic is it's undecidable in general. So most of the effort here is to find out a fragment of first-order logic that is still decidable and can express ontologies. There actually are many different incarnations of this concept, like semantic networks, frames, description logics, and RDF, RDFS, OWL, that is more recent in the semantic web work. Okay. All right. So, what is the actual main ingredient in ontology? Well, basically, we are talking about something like object-oriented programming, where you have individuals, categories, class, and relations. So if there is a member from the class, then the member inherits the properties of the class, and the members are related to another member through some relationships. And some people view ontology as a taxonomy. So if you have a taxonomy of biological family, so like genus or those, I don't actually remember all those terms in English, but you see what is the thing? You go start?
Phylum, like genus.
Yeah. Okay. So that's a taxonomy too, right? So that's what you see. I mean, that is actually used in many places. If you go to library, there's also taxonomies, right? You go into some way of specifying which section is to have what kind of books, and medicine as well, and biology, same. Okay, so yeah, you can just read this. I'm not going to go on this. Now, semantic web was designed having this ontology in mind, and the basic idea here was to build this layer by layer. So if you have to start with some common vocabulary. Okay, when you talk about some knowledge base, you should have common vocabulary, right? So first, you have to say how to code this. There's some Unicode that you have to work on, and everything has a unique name so that you can actually refer to. Then there is some XML that helps a machine to read or understand what is this content of this field. And then they talk about RDF, which is to basically how these entities are related, okay, or connected. And then build some ontology based on this graph. There should be some logic and then proof and trust. This was the original idea of building the semantic web, so people start with working from bottom up. And around this layer, when this layer was actually being done, it got distracted because research doesn't work always as planned, right? So it turns out that the ontology layer was hard to debate. Okay, so what to put into the ontology layer? Basically, it was not about really the new research area to pursue, but rather how to standardize those existing work in the research. And people have different ideas on that. So yeah, so what was happening here is actually changing evolving into this different way. So there's RDF core. Okay, so at that level, what happened was OWL is supposed to be the ontology language, web ontology language, but then it becomes a bit too slow. And OWL version 1 was not really that expressive. Okay, so people were waiting for next version, but that's too long to wait. So what happened was there's something called RDF schema. We are going to look at RDF and RDF schema today. Basically, the idea is you want to have a bit of ontological construct, and somehow that seems to be okay for many of the applications. So people didn't wait until the OWL emerged. So they are just okay with RDF schema. Okay. Now, also what happens is instead of OWL, people also find that rules are also easy to use. Sometimes OWL has somewhat limited expressivity because to capture the decidability issue. What happens in the OWL-like language is if you have this construct that is decidable. Now, once you add one more construct, suddenly the language becomes undecidable. That happens quite often. So there are many fragments of OWL that is decidable but has different construct. Okay. So and on the other hand, people thought, well, why don't we just forget about OWL and just going into the rules, and we can do the same thing or maybe more expressive things. Okay, so what is the idea of RDF? So we want to express a very simple concept. Note here that this is not really difficult to do in any logic. It's just that what is actually standard way that facilitate the encoding effort. So if you want to express that pen number 7 is red, what can you do? Then you can write red of pen 7, right? So to say that pen 7 is red. Now it's easy to ask what is red. Say in the QA system, you can say red of X. Okay, so this is called conjunctive query. You want to bind X with the instance. So if you ask this query, okay, so like this query, then the system will answer like red and pen 7. And you see this X is now bind to pen 7, that's the answer. Okay, that's good. The problem is, now if you want to ask the different direction, you want to ask what is the color of pen 7, this becomes difficult. Okay, because this X ranges over the object, the argument, right? It doesn't actually range over the predicate. If you actually want to range over the predicate, that becomes actually the second order logic. It's no longer in the first order. And second order logic, of course, harder than first order logic. Okay? All right. All right. So then people thought, well, let's now introduce these color predicate. So then you can say what is red, and also we can say what is the color of pen, because they are kind of symmetric, right? So that is good. But then if we want to ask what is the relationship between pen and red have, what is the relationship, then it's difficult to get this. Again, the same reason that color is not quantifiable. Okay? You cannot ask about the color. So the natural idea is let's introduce very generic predicate called prop. It's about any generic property, and having this in terms of 3 terms, ternary predicate. So pen 7 has a color of red. And then now you can talk about any of them. Given these two, you can talk about what are the objects that has red color. Okay, you can return pen 7. Well, what is the relationship between pen 7 and red? Then it should be a color, and also vice versa. So you can have what is color of pen, then it's red. Okay, given the two, you can query the other. And turns out that this is actually enough for many of the applications. Okay. So this is actually the standard form: prop, object, property value, or sometimes you can say prop, subject, relation, or subject, predicate, and object. Okay, so there is actually different terminology, but what is important is this is quite simple to do. Okay. Now you can also introduce some other concept like A is a parcel. Okay, so some object A is a parcel. Then you actually need some special instances. So what do we mean by either? Okay, so that has to be some predefined property. So we say type. Okay, this is not a user-defined term. So type is the reserved property name. So A is a type of parcel to say that A is a parcel. Or you can also write this way: A parcel true, where this parcel has a Boolean property. Okay. Okay. So that's actually quite universal. Now the problem comes when you have to represent something like this. So section 2 of course CS 422 is scheduled at 10:30 in room CC 208. Now this is one way that you might write in ASP fact that has now 4 arguments. How can you do that in this RDF that has only 3 arguments? So what people found out is, let's introduce some generic name for this whole predicate. So let's say B123. So instead of one fact, we are going to say this property. This is kind of so-called reification. Okay, so introduce some kind of auxiliary node. And this, from auxiliary node, you have course CS 4022. Okay. Section is 2, time is 10:30. Okay. So it turns out that if you do this way, you can express any complex conjunction. Okay? The only problem is, of course, you have to do this reification, and sometimes you can write this easily. You have to break into many lines, but who cares? Okay. The nice thing about this is because it can be actually understood in terms of graph theoretic way. So instead of these things, so this prop is a very generic thing. So object property value, object property value. Okay. So the three things. Three argument corresponds to node, edge, node. And turns out that graph is actually very powerful, KR formalism as well, in the sense that you can actually link all these constructs, and somehow these are all connected. So you can say, like, this is subject relation and object, or property and what is terminology? Object property value. Okay. So here you can say, well, comp, maybe this is particular computer name, 2347, is a model of Lemon laptop. It's owned by Craig, whose room is R107, which is in the building computer science. Okay. So by connecting these things, you can actually connect a lot of knowledge. Okay, and what happens is, of course, you don't have to build a huge knowledge base from the beginning. Some people only build this part, some people only build this part, but then you can connect it. You can merge them to talk about those things. Okay, so that's actually quite an interesting idea. Now, this is RDF. How do we turn this RDF into ASP? It's quite simple. It's just this, right? We already saw. It's just a fact. There are a bunch of facts. There is actually no rule. Okay? You say prop this subject relation object. That's it. Now, one thing to note here is there's actually no meaning of these symbols. You just write any thing here, deliver to model. But what is the meaning of deliver to? What is actually brand, logo? What is the meaning of color? There's nothing in RDF. RDF itself is just a structure. It doesn't give any meaning. And it is okay because that was supposed to be the goal of RDF. It's not an ontology language. Okay? However, this is where the RDF schema comes in. So RDF schema is actually not an extension of RDF. Actually, it's a restriction of RDF. It's not a new formalism, but it's just some more structured way to talk about RDF. So what happens in the RDF schema is not really the schema of RDF, but it's just adding some pre-specified predicate. Okay. So what are they? I don't know whether you can read. Can you read this? Yeah. Okay, or maybe I can. Okay. So in RDF level, you have everything there. Doesn't matter what that means. Okay, you can introduce any predicate. In RDFS, is actually based on RDF. You can use these designated predicate. You can talk about these predicates has the domain and the range. Domain of rent is a person, and the range of rent is a residential unit. And this domain and range has precise semantics. You don't actually define it. It's actually given in the semantics of RDFS. And you can also say about subproperty of. So actually, let's look at subclass of first. So apartment is a subclass of residential unit. Okay, it's like object-oriented programming. You have a subclass relation. Okay. Another thing is not here, but okay. Another thing is a subproperty. Now, not only the class has subclass relation, but the predicate has subproperty relation. Okay, so besides that is a more general concept of rent than the rent, right? So besides that could be actually owns, can contain the owns relation as well as rents relation. Okay. So this these two are the predicate, but this predicate contains all the extents of the lower predicate. Okay, so that's what you can do. That's somewhat different from the object-oriented programming. Okay, so then the question is, how do we understand this meaning? How do we actually define the meaning of the subclass of this domain and range? Well, you can do that in formal language, like in ASP. So what do we mean by this is we are going to, how do we define the meaning? We just add a bunch of rules to talk about this. One thing is here. So let's say this class C, the C is a class name, and the object is a type of this class. Okay? Now if this class has some property n, then object will also have the property n. Right? So if class has property n, then every object that belonging to that class also has the same property n. And that can be expressed by a simple rule like this. Okay? So if the object is, so suppose you have this arc from class C with a property p to value n. So suppose you have this link here. Okay? Then we want to also say that object with that object of the class also have the same value n. It can be expressed by this rule. So if the object is a type of class, then object will also have the same property with same value. Okay? So let's think about some example. So let's say we have lemon laptop 10,000. Okay? So this is some object, right? And you can say that this is actually class, actually. You can have class. So this one means, so this has some property. So let's say this laptop has lightweight. So you can express this way, right? Okay, from in the RDF way, you can say this class has weight that is light. You can also say this computer, this laptop's packing is cardboard box. Now, I know some particular computer, so let's say C1, okay, is a lemon laptop computer. So what I want to do is just introduce the note here that C1 is a member of Lemon Laptop 1000. But once I introduce this link, according to the semantics of the logical property, what we get is, since this is a type of this Lemon computer, it will also have the same packing as this class, according to this rule. So every C1, I mean C1 is actually a particular computer, as long as we know that this is a type of Lemon Laptop 1000, we know that it is lightweight and its packing is cardboard box. And you can do with many other computers here. Okay? Are we together? Yes?
I have a question.
Mm-hmm.
Why is lemon laptop the center instead of X being as the object?
X is any object.
Oh.
Right? So here, this one means this is subject, predicate, and object. So there's if there is a link from X to this edge from X to Lemon Laptop 1000 labeled with type, then X's weight is also light. That's what it says. Okay, so you can instantiate this with C1. Now, as I said, the X can be anything, right? So you can have any members of that class. Okay? All right. Phew. And now we can actually talk about more things. Actually, there is. Okay. So the next slide is you can also do the inheritance from the subclass relation. So if S is a subclass of T, okay, and you know that X is a type of S, then you can also say X is a type of T, right? So in that sense, you can have introduced, say, subclass of relation. Now, if you know that this is a subclass of, let's say, lemon laptop, not the 10,000 part. It's a lemon laptop. By declaring this, you also, let's say, this has manufacturer to be the lemon. Okay. Now you can see that with the rules that we just saw, C1 is, of course, lemon laptop is a type of lemon laptop 10,000. But now with this link, we also know that C1's manufacturer is lemon. Okay, because this is actually a rule that guarantees. Because if X is a type of S and S is a subclass of T, we can also say X is a type of T. Okay, so if C1 is a type of lemon laptop 1000, lemon laptop 10,000, and lemon laptop 10,000 is a subclass of lemon laptop, then X is a lemon laptop. This is what the rule says. Okay, so the meaning of these predicate is precisely defined in a formal way, and you don't change that. This is actually another example where you can see that there's a minivan. Minivan is a subclass of van, and van is a subclass of motor vehicle. Okay, so you can have all the class hierarchies. Okay, and as long as you define some property here, that can be inherited to all the way down. Okay. All right. So I have a few minutes. So this is actually non-technical slides. So recently there has been a lot of work in developing very large ontologies that captures various areas of human knowledge and deploying this knowledge in applications such as search engines or question answering. So one of the examples is Watson system that uses this kind of ontological fact. Okay, and so these are the examples: Psych, WordNet, DBpedia, Yago, Freebase, Google's Knowledge Graph, and Taxonomies. In fact, the terminology, the term knowledge graph is actually very confusing terms. So, in fact, what happens was Google introduced this term to talk about their big proprietary format, their company's product. But then people also started to use this terminology for any graph-based knowledge languages like RDF. And so today we see all the mixed up. And I don't know whether you can read it, but let me say. So these are the definitions of knowledge graph from different sources. So the first one is saying that a knowledge graph mainly describes real-world entities and their relations, interrelations organized in a graph, define possible classes and relations, allows for potentially interrelating arbitrary entities with each other, and covers various topical domains. So this is one attempt to define knowledge graph. Other things are knowledge graph are large networks of entities, types, properties, and relationships. Okay, knowledge graph could be envisaged as a network of all kinds of things which are relevant to specific domains and organizations. And another thing is we define a knowledge graph as an RDF graph, blah, blah, blah. Okay, so what is the common in this definition is basically it is about some graphical representation of knowledge. So it requires. Here is one summarized. A knowledge graph acquires and integrates information into an ontology and applies a reasoner to derive new knowledge. That's actually what we do in knowledge representation. Okay, so there are a couple of examples of knowledge graph. which I will probably introduce next class. Okay? Any question about today's materials? Okay. All right, so then let me open the Socrative.